All right, let's talk about something really mind-bending. For 200 years, there's been a type of math problem that was officially, impossible to solve. It was a hard wall in our understanding of algebra. But now, a monumental claim suggests that wall has just been smashed. Today, we're diving into the story of this 200-year-old problem and the person who claims to have finally solved the impossible.
This line, right from the source of this incredible claim, just sets the perfect stage, doesn't it? It's a direct challenge to a boundary in mathematics that's been accepted for generations. It kind of whispers that we might be on the edge of a huge shift in what we thought was even possible.
So, to really get why this is such a massive deal, we need to jump back in time a bit. For centuries, mathematicians have been wrestling with these things called polynomial equations. You probably remember them from school. But as they got more and more complex, a wall went up, one that seemed completely unclimbable.
This timeline really puts that 200-year gap in perspective. Back in the 1500s, progress was being made. They figured out third and fourth degree equations. But then, bam, a full stop. In 1824, a brilliant mathematician, Niels Henrik Abel, proved there's no general formula to solve fifth-degree equations using standard algebra. And for 2 centuries, that was the law of the land in math. Until now, maybe.
This is the Goliath of our story, Abel's impossibility theorem. What it basically says is, once you get past equations of the 4th degree, you can't create a single universal key, a formula using tools like addition, subtraction, and roots that will just unlock the exact answers for all of them. It's kind of like saying you can't build a skyscraper using only a hammer and nails. The tools themselves are just too simple for such a complex job. And this idea became a cornerstone of modern algebra.
So why the dead end? Well, the source breaks it down into 4 reasons. The tools were just too limited, the equations got ridiculously complex, and because of that, mathematicians had to settle for just estimating the answers. But that last point, that's the real kicker. Abel's proof was that it was impossible within a specific set of rules. It's like saying a door is locked. Sure, but only if you're trying to use a specific set of keys. What if there's a totally different kind of key?
And that brings us to the David in this story. Enter Professor Mourad Sultan Ezouidi. He's an internationally recognized mathematician who claims he's found a way to work outside of that old, narrow framework. He says he's developed a new method to do what was long thought to be, well, impossible. And his claim is not a small one. He hasn't just chipped away at a little 5th-degree equation. Nope, this work claims a complete, exact, and verifiable symbolic solution for a polynomial of the 20th degree. I mean, that is an incredible leap, just blowing right past the historical barrier.
In his own words, Professor Ezouidi sees Abel's famous theorem not as some final, absolute endpoint, but as a historical milestone that we've now passed. This view just completely reframes the entire story of algebra, from one of limitation to one of endless discovery.
So just how different is this new approach? Let's actually put the classical methods and Ezouidi's theorem side by side to really see the revolution that's being claimed here.
This chart just lays it all out, doesn't it? It really highlights the clash of ideas. On one side, you have the old guard, impossibility, relying on close enough answers, and a philosophy that just accepts certain limits. And on the other side, you've got this new claim, exact solutions, a whole new theoretical foundation, verifiable accuracy, and a philosophy that flat out rejects those limits. It's not just a new method, it's a whole different way of thinking about the problem.
Okay, so the big question, how does this new method actually work? If it's not using the old tools, what's the secret sauce?
So the crucial idea here is a total shift in perspective. Instead of us trying to force a solution onto the equation using outside tools, this method creates a framework where the polynomial actually reveals its own answers. Think of it like a puzzle box that has the instructions for opening it written on the inside. You just have to find that first little step to get it to start unfolding itself. And at the very heart of this process is this, a universal recursive formula. Now, we're not going to try to solve it here, but its existence is the key. It represents this repeatable, structured engine that you can apply to any polynomial to start that process of uncovering its own roots, one step at a time. And this path right here is just brilliant. You start with your big, complicated equation. You apply this new formula to calculate a series of symbolic coefficients, moving step by step. And by following this chain, you arrive at the exact symbolic roots. No guesswork, no estimation needed, just pure algebra.
This is really the bottom line. The classical approach after Abel could only give you an approximation, an answer that's really, really close. Ezouidi's claimed approach delivers symbolic precision, the exact answer spelled out in pure algebraic terms. It's the difference between measuring a shadow on the wall and actually holding the object that's casting it. Now, if this claim holds up to all the scrutiny from the wider mathematical community, the implications are just profound. This isn't just about solving one tough problem. It could signal a whole new era for algebra itself. And why does that matter? Because solving these complex equations is absolutely crucial for fields from physics and engineering to cryptography and economics.
And here it is, the biggest takeaway from the source material. The deep philosophical implication is that unsolvability was never really a property of these equations. Instead, every single polynomial, no matter how complex, already contains the complete blueprint for its own solution. We just never had the right key to read it.
This visual really captures the whole journey. We could be moving from a world that had to settle for close enough to a world that can achieve exactly right. This isn't just a small step forward. It's a complete paradigm shift in how we approach these fundamental problems.
So we're left with this massive question. The mathematical community is going to need time to review, to verify, and to debate these findings, for sure. But if it's proven true, this work shows that even the most stubborn limits are sometimes just milestones, waiting for someone to come along and surpass them. The final word on Abel's impossibility might not have been written in 1824 after all.